Calculus! This is AP Calculus! Lesson 9-2. Approximating total change. Today's date is Monday, February 11th. Sorry, Rochelle. Alright, so visual integration. So there is a definite change between infinite and the finite. This whole unit, I know that Arrow led us yesterday, but I'm going to definitely reteach a little bit of stuff. Yeah. This whole unit is based on incomplete data, on finite data. Here's a graph of infinite data. Infinite data is given to you on the AP test in the form of an equation. Finite data is given to you in the form of a table. And as Arrow said yesterday, you don't know what happens in between these points, and that's very accurate, and that will help you on a bunch of multiple choice questions. By the way, here we are in Unit 9. Notice that we're almost done with our lessons. We're on 9-2. Arrow did 9-1 on Friday. We're doing 9-3 tomorrow. And then you can see we're doing self-check on Wednesday, self-check on Thursday, and this pre-test on Friday, which means Monday, Tuesday, test is on Tuesday. Yeah, 2 self-checks. Only 3 lessons. It's that easy, yes.
No, that's not good at all.
That's not good at all. Okay.
All right.
We're going to be on break for that week.
Yeah, I know.
So we're going to forget some stuff.
I realized that, and I had it planned out so you took the test on Friday, and then those 2 snow day happened. So now those 2 days happen after.
But
Yeah,
it's
we're
only
not going to be here on Thursday.
You're not here on Thursday? Who else is not here on Thursday?
It's only Arrow.
So Thursday, we will have a very hardcore good video of the self-checks on Thursday for you to check your work for Friday. But I expect you guys to be able to do that at night on Thursday to get ready for the pre-test on Friday.
When's Montreal coming back? Is it just Friday?
They come back on Friday. Yeah, they're only going up to Bridgeport and then coming back.
That's encouraging. Okay, that's good.
All right, and happy Valentine's Day is on Thursday also. So visual integration. So infinite data. So whenever I have infinite data, I technically have an infinite number of bars, right? Infinite number of rectangles. Just draw these lines on your notes. Let yourself know there are an infinite number of these bars. In fact, that's where the definition of an integral comes from. Let n go to infinity of this Riemann sum. And I haven't talked about a Riemann sum. Well, I might have mentioned it before, but definitely today is where we first do our Riemann sum. What is the first Riemann sum I can tell you about? Well, let's show you what a Riemann sum looks like. And you get to choose doing a left Riemann sum, a midpoint Riemann sum, a right Riemann sum. This is going to be a left Riemann sum, because I'm using the point on the left and drawing out a bar that goes to the right. And I'm making a rectangle. This rectangle obviously is way, way thicker than infinite data. Infinite data has infinitely thin rectangles, but finite data has these giant wide rectangles.
It's like 4K versus 144p.
Yeah. This is 144p, the resolution of a really bad YouTube video that you can actually count the pixels, and this is the 4K where I think iPhones now record in 4K. Is that true, Ben?
I don't know.
I can neither confirm nor deny because I have a flip phone. Okay, so so this is our finite data. It is very pixelated. It has a ton of bars, but it's a pretty good approximation still, right? It's better than just doing an approximation of a giant triangle or something. It's just a bunch of rectangles. And rectangles are super easy to find the area for. Rectangle is just base times height. It's really easy to find the individual areas of these rectangles. So far, so good? This is the way that we're going to approximate our infinite data because we only have a table. And there are a few different ways that we can do this. And you can kind of see that we're going to have this table. Oh, we have the table on the next note. So on our next notes, you'll see this table where we do a left sum, a right sum, a midpoint sum, trapezoid sum. That comes tomorrow. Today, we're just learning about a left Riemann sum. And I think a right Riemann sum. But we're eventually going to be learning all of them. So we're going to use...
Last year, this was all on one day. Was it?
Nope. Last year, it was definitely 2 days. Yeah. So this guy, how would I say what's happening in this graph? This graph is really the exact integral. Oh, come on now. The integral from A to B. We're calling this thing g of t, capital G of t. So capital G of t, dt. That is the definition of an integral. This guy is only approximately equal to, so I'm going to do my, by the way, if you're using LaTeX, this is slash APROX, but you guys don't care about LaTeX. It's the proper way to find or to write up your notes from A to B. I had a friend in college that actually did all of his notes in LaTeX. He was a cool guy. G of t, dt. So this is only approximately, this is exactly equal to. And of course, the more rectangles you have, the closer you get to the actual integral. All right, so let's finally do our first Riemann sum, a left Riemann sum with 3 subintervals. By the way, whenever I say 3 subintervals like this, that means that there are 3 in-betweens. In between, in between, in between. There are 3 in-between areas, 3 subintervals. Your first interval is going to be the interval from 0 to 1. Your next interval is going to be between 1 and 3. Your last interval is going to be between 3 and 7. We can all nod our heads. That is pretty self-explanatory. Okay, so let's go ahead and graph this to see what's happening now. 0, 6, graph. 0, 6, boom, there's a point. Graph 1, 8. 1, 8 looks like there. Boom, make a point. Graph 3, 12. 3, 12. Boom, make a point. And graph 7, 18. Boom, making a point. All right. So from this point, I'm using the leftmost point. This is key because we're going to do a right Riemann sum in a sec. The left point, and from that left point, I'm going to make a bar until we run into the x-coordinate of our next point. That's our first bar.
Oh, so if you do it from the left, that's an underestimate. From the right, for this one.
Whoa! Say it again. That is so cool, Ben. Yes, say again.
So from the left, at least on this kind of function, is an underestimate. From the right's an overestimate. So if we do the average, shouldn't it be very close to the actual?
That is true, yeah. In fact, if we can get really close by doing something that we'll talk about tomorrow where we do midpoint, which gets a little bit above and a little bit below. And even better would be using a trapezoid. Anyway. Yeah, so let's go ahead and do the next bar. So I'm using the leftmost point, making a bar that goes out to the right from that point. There's our next bar. Using the leftmost point, making a bar that comes out and makes a rectangle. Using the leftmost point, and we don't care because we only want 3 subintervals, so I have 3 of these rectangles. So far, so good? There's my graph. That means this point right here, this 18, we don't use. Cross it out in your notes. We don't actually use that guy. We do use the 7 because we need to know where to end the interval, but we don't use the 18. This point up here, the height of 18, we don't use.
How would you feel if someone said, hey, we don't need you now?
We don't need no edu. Oh yeah, that works better. All right, so here is the approximation. So let's go ahead and calculate this thing. What is the area of this guy?
6.
It is 6. What about this one? 2 by 8.
Okay, that's 16.
This is 1, 2, 3, 4 by 12.
48.
Michelle's killing it. Yep, 48. And we just add those up. That's our answer. That is the answer of the approximation.
It's 5 by 12. 60.
No,
It's 4.
2 to 7.
It's 4.
I just drew this out.
Oh.
3, not 2.
Yeah. It's good to get these errors out while we're doing the notes, let alone the test or the AP test. Get the errors out now, right, guys?
Yeah.
We always said that when we were in basketball, like when you were doing the warm-up and you missed a layup, it's like, we got the miss out now. We're not going to make the miss in the game.
Okay, that's different.
Right. So what was actually happening here? What we were doing was base times height, repeated and repeated. So what we're really doing, and I'm going to write this all out so you can have it in your notes, 1 was the base and 6 was the height. I'll even take the liberty of saying, we'll write this like this. This right here was the base, and this right here was the height. This will get a little bit tricky, especially when we talk tomorrow. Tomorrow we're talking about midpoint and trapezoid sum. Those have slightly different formulas, although left and right Riemann sums are pretty close to being the same. And then we added this with 2 times 8. The base was 2, the height was 8. And then this is going to be the base was 4, the height was 12. And add those together, that's going to be 6 plus 16 is 22. 22 and 48, that's 70. And this is equal to 70. And what were our units? Did we ever have? Oh, I do see the units. You guys see it in the table?
Feet per hour.
Is it feet or is it feet per hour?
It's feet.
Why is it feet and not feet per hour?
This is a graph of something.
Wait, what?
Slope or something.
So when we're asking why is our unit feet and not feet per hour when L of t is feet per hour, and it has to do with this symbol.
Because
Oh gosh.
Because L of t is the graph of the slope of L. No.
Whenever you go backwards, just get rid of an hour. Every time you go backwards, just get rid of 1 more hour. So if you had hour squared, get rid of the square. You just have 1 hour.
I didn't even go backwards.
You're going backwards because the integral is going backwards. The derivative is going forwards. So if I had d dt of L, then it's feet per hour per hour. You just add on another hour or divide by another hour.
What about plus C? At one point we had plus C. I forgot about that.
Yeah, so we had plus c whenever we had a non-definite and indefinite
Oh,
integral
yeah.
when we didn't have bounds. When we do have bounds, then the c gets canceled out. All right, so Ben told us that this guy is an under approximation.
Yeah.
Because what was really happening here, go ahead and sketch this out also. What was really happening here is we had this function that looked maybe, I don't know, sketch it. It looked like that, which means all of this empty space means that we have error that makes this an under approximation. So we're going to say this approximation, and it is an approximation because obviously we don't have infinite number of rectangles. I can't spell approximation. This approximation is less than the actual integral that we're finding, than the integral from 0 to 7 of L of t dt. But why? And here is the reason that you're still forgetting. And let's do something else to get this approximation. I gave you another graph here. Let's assume that this was a decreasing function. So let's go ahead and make a point, I don't know. Well, let's make 118. And then let's do 020. I forgot 020. 118. Let's do 312. It doesn't really matter. It just needs to be decreasing. And then let's do 7, 6. So those are our rectangles now. And I have the line too. I don't know why I'm not using it. There we go. So I have a bar there. Oh. And then I have a bar that goes like that. And then I have a bar here, and then a bar that goes like that.
So that one's going to be greater than?
Mm-hmm.
Why? You're right, but why?
Because you're going out more than where the line would be.
Exactly, yeah. So if I were to sketch this line, it doesn't matter about the concavity. It matters about whether it's increasing or decreasing. This could have been concave up or concave down. But what really matters if it's increasing or decreasing. Let's go ahead and say that this one was decreasing for the whole interval. This one was increasing for the whole interval. So this one was less than, or it was an under approximation. It's probably, we can write that above here, under approximation, if you don't like to write all this out. This is an under approximation. Under approximation.
You wrote approximation.
Ay, ay, ay. My computer is not like me. And what is our reason? Our reason has to have increasing or decreasing. Who wants to say it? So this is an under approximation because our function is increasing. And we have to say on what interval. So what was the interval between 0 and 7? So increasing on this interval from, I guess technically it's only increasing with parentheses, not square brackets on 0, 7. So that is the key part. This will be on the self-checks. This will be on the pretest. This will be on the test. I will ask you, after you calculate that Riemann sum, it'll be a right Riemann sum or left Riemann sum, something. Is that an under approximation or an over approximation, and why? And here's your answer. It'll be an under approximation because it's increasing in this case. If it was decreasing, then it would be an over approximation. All right, on to right Riemann sum. We're on the back. All right, so we're going to approximate, again, L of t. We have our table here. Let's go ahead and see what it looks like graphically. So 0, 18, graph that point. 0, 18, 1, 12, 3, 8, and 7, 6. That was the same data, wasn't it? It was the same data. No, it's backwards. Okay. But now it's a right Riemann sum. So that means I'm using the rightmost point and making a bar that comes out to the left. So I'm using the rightmost point and making a bar that comes out to the left. So that's what it should look like. Does everyone have those bars? I'll make these points really big so I can see them easier. Which height did we not use?
6. I mean, yeah.
It was 18, which is interesting, right? So a right Riemann sum doesn't use the left point. A left Riemann sum does not use the right point. That's very important to know, especially to check your work. You're like, wait a sec, I used the height of 18 in my formula down here when I'm writing out my work. That's a bad thing. All right, so when I'm doing LFT, let's go ahead and calculate the area of all of these. Area of the leftmost rectangle is 12. It's 1 by 12, which is 12. So I'm going to write out what we just did there. We did 1 times 12. Okay, the next one is 16. And we did what times what?
8 times 2.
Yep, base was 2, the height was 8. And then finally, we have
6 times 4 equals 24.
Yep. So 1, 2, 3, 4, a base of 4, a height of 6 to get 24. So add all of those together and we get what? So 24 plus 16 is 40. 40 plus 12, that's 52. Is that what you guys got also? 52. What are our units?
Feet again.
Yeah, feet. All right. So this function right here, was it increasing or decreasing? It was decreasing. And I mean, it's pretty clear when you graph it out that this is going to be an under approximation because we have all this gap here, gap here, gap here. So it is an under approximation, and the reason is because it's decreasing, which is that the same reason for up here? Up here we had decreasing and it's an over approximation. Here it's decreasing and it's an under approximation. So a right Riemann sum and a left Riemann sum have opposite rules. They flip. And again, if you want to see a quick picture, go ahead and just make a quick graph. It doesn't have to be like mine. Just make something that is increasing. So here's my increasing function, chunk, chunk. And then I'm going to go chunk, like that. Oh, I guess I can stretch that out.
Is this a right sum?
It's still going to be a right sum, yeah. So this is still a right sum because I'm using this, use blue. This is the rightmost point, and rightmost point that I'm using, and then maybe I had like a point right there. I'm using the rightmost point. This one is increasing now. So there's my line that goes through it. It's increasing, but this is, come on now, computer. It's increasing, but now it's an over approximation. So that is definitely going to be something that you're going to be writing for your summary. But we want to say, is it an over approximation or is it an under approximation for our final answer?
For the one with decreasing?
This is just a random one just to show you what happens when you have a right Riemann sum that's increasing. For the one that's decreasing,
It's under?
so let's write it out. This is the minimal that you need to write to get the point. Under approximation. And why?
Because LFT is decreasing from 0 to 7.
On 0, 7, yep. Good.
You need to put units somewhere.
Oh, yeah. Hours?
You don't have to put units on the explanation. No. I understand where that's coming from because usually we said, what does this integral mean? And it's like, oh, it's the integral of this function. So it's the change in people from 0 hours to 7 hours. But on this explanation, you just have to say that it's decreasing. And to be more specific about where it's decreasing, we say between 0 and 7. You don't have to have units on the explanation. That's a good question. Oh, yeah, I forgot about this guy. Midpoint sum. All right, so midpoint sum. This guy's fun.
Does
For-
it mean like the middle one's not gonna?
The middle one, what?
The middle one is not gonna be used.
It's actually the reverse. Only the middle one is used.
Oh,
Let's go ahead and graph these points really quick. So 0, 5. Boom. 1, 8. there. 310 is right there. 412 goes right there. 613 goes right there. 718 jumps all the way up there, and 920 right there. Okay, so everyone has these points, yes? All right, so now what we're going to do is we're going to go every other one, essentially. So don't do the first one, but do the second one. Circle it. Don't do the third one, but do the fourth one. Oops. All the even ones, essentially. And then that one. So I'm going to have 3 of these different heights that I'm going to be using. Let's circle all the heights that we use. We use the height of 8, we use a height of 12, and we use a height of 18. We're going to use that as the height, which means that when we make our bar is going to be that height from this interval between 0 and 3. So here's where our bar is going to look. Between 0 and 3, there's our height. Between 3 and 6, there's our height. Between 6 and 9, there's our height. And then, of course, I need to actually make them rectangles, so rectangle, rectangle, and rectangle. And I should make my points bigger in my notes so you can see what's actually going on. All right, so there it is. That's what a midpoint sum looks like. And then go ahead and just do a quick little sketch of what's going on between each of these points. All right, the question here, is it under approximation or over approximation?
Looks about good.
It looks pretty close. And I don't think they will ever ask you, oh, they might. So if they gave you an actual function and then told you to find a Riemann sum of it, then they'll ask you if the midpoint sum is an over approximation or under approximation. If they gave you a table, just like I did here, they will never ask that because you can't tell. You're like, well, it looks pretty darn good, and that's as good as you can give them. All right, so let's find the area of each of these. Area of this left one, what are we multiplying together? The base was base of
3 times
height of 8. 3 times 8 is
8,
24. So this area here was 24. Come on now, 24. Next one, we're going to add base was
36.
3 times 12. So base of 3, height of 12. And Rochelle told us 3 times 12 is 36. And finally, our new base is
54.
3, and then the height is 18. And 3 times 18 is indeed 54. I add those together. 36 plus 54, that's 90. 90 plus 24, that should be 114. So that means this is equal to 114 what?
Feet.
Feet, yep. And there it is. There's a midpoint sum. You need to be able to do all those, at least be able to sketch them so you can really see what's going on. In terms of showing your work, for the AP graders, they want to be able to see your steps. If you just do 114, I don't think you get full points. You need to either write out your formula like this, or you need to write individual areas on a graph. I don't think they give you a graph, though.
What if you graph?
If you graph it and then show the areas of each of those parts, then you get the points for the intermediate step, but you have to show your work somehow to show where 114 came from.
You didn't give us graphs in the homework.
I did?
No, you didn't.
I didn't? All right, then that means you're writing down base times height, base times height. And you can get there because what were we really doing? We're doing 0 and 3. 3 minus 0 is 3. That's where the base came from, times the middle point. Then for this one, we did 7 minus 4. 7 minus 4 was 3. And then the height was this middle height.
Oh, it's not
That's
the midpoint,
confusing.
but it's somewhere in the middle.
This, it happened to be that way, but I messed this up. 3 and 6. 3 minus 6 is 3, and then 12. And then finally, 6 and 9. 9 minus 6 is 3 times the middle point of 18. So that's what it looks like in terms of the table. You do the sides and then do the middle. Sides, middle, sides, middle. You have to subtract the sides. All right. So the graph was kind of a crutch, but we should be able to do this just by looking at the table. We did 3 minus 0 to get 3. All of them were 3. They just happen to be nice, easy steps. Same thing up here. You should just be able to look at a table and say, okay, well, you're going to really do 1 minus 0 times 12, 3 minus 1 times 8, 7 minus 3 times 6. In fact, the general shape, I'm going to be going over this tomorrow as well, but the general shape for a right Riemann sum is with the little tail here on the right. The general shape for a left Riemann sum is a general little tail here on the left, or you can think of it as maybe a gun with a handle on the left, a gun with a handle on the right.
Censored.
Okay, that's not a guess.
Censored. Oh, we're in school, so it's a tail. And then this one, I don't even know what shape this is going to look like. Some Martian lander where you have the sides and then connected to the middle. It's a V. You're doing V's over and over. V, 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 V.
If we think about it in terms of resolution, like the midpoint sum is like when it's really terrible resolution, but you just move farther away, so it makes more sense.
Okay, yeah, I mean, if it makes sense for you, definitely use that. Are there any questions? All right, go ahead and write your summaries now.